Hello everyone. In this video, we are going to see the singleton AEM equation for the different modulation index and how we are going to generate this equation using a platform called GeoGebra. So in our previous video itself, I have explained the term AEM modulation and the modulation index and how to use the GeoGebra platform. So in this video, we have quickly refreshed this concept. So AM modulation is nothing but the amplitude of the carrier signal is varies in accordance with the amplitude of the message signal. So this is our message signal and this is our carrier signal and it is our overall AM modulated wave. So here this imaginary line is called the envelope. So this is the definition for the AM modulation. And now we are going to see the formula for that. So this the message signal formula where m of t is equal to am cos omega mt. So this is our carrier wave formula. So c of t is equal to ac cos omega ct. So this is our overall am modulated signal equation. So ac cos omega ct into 1 plus me into cos omega mt. So in our previous video, we have generated the waveform for this equation. And now in this video, we are going to generate the waveform for this equation. So now we can see what is the difference between these two equations and how to derive this waveform. So the AM modulated signal can be written as so AC into 1 plus m of t into cos omega ct. This m of t can be written as AM cos omega mt. So after in multiplying it, we can get this equation. So this is looking like cos A cos B, but 1 2 is missing. So multiply and divide by 2. And now we can apply this equation cos A plus B plus cos A minus B. So after applying this equation, we get this formula. And now we have to multiply and divide it by AC. So that AM by C we can get, and this nothing but our modulation index, that is MA. We can also written this as mu. So mu is nothing but AM by AC. And this omega can be written as 2 pi f. So that we can get this final equation. So here we can get the three different term, carrier, upper sideband and the lower sideband. So this is the difference between the previous equation and this equation. So in the previous equation, we can't differentiate the upper sideband, lower sideband like that. And but in this equation, we can get the three terms. And now we have a question. So whether we get different waveform for this two equation. But the answer is no. We are going to get the same waveform for this two equation. So now we are going to see how the waveform will be differ for the different modulation index. So when the modulation index is 0.5, the waveform will be looking like this. So observe the shape of the envelope clearly so that we can understand when we are generated in the GeoGebra. So here the envelope is looking like this, and this lower signal is doesn't touch this origin. So when the modulation index is 1, we can get like this. So here the minimum amplitude is touching the origin. So when the modulation index is 1.5, the upper signal and lower signal are overlapping, so that we can get one extra sideband. So here also clearly observe this envelope shape. So in the next slide, we are going to see the equation which we are going to generate in GeoGebra platform. So those are overall AM equation, so which we derived in the previous slide. So in this equation, I substitute AC is equal to 2, omega C is equal to 100, and omega M is equal to 5. So and for the different modulation index, we can get this equations. So like S of t is equal to 2 cos 100t plus 0.5 cos 105t plus 0.5 cos 95t. So like that, we can get the equation for when mu is equal to 1, when mu is equal to 1.5. And now we are going to realize this equation in the GeoGebra platform. So this are a GeoGebra platform. So first we are going to generate this equation. So here we can observe the AM equation when the modulation index is 0.5. So there is an under modulation signal, and here we can observe this lower amplitude doesn't touch the origin. And also we can observe the envelope shape, which is similar to what we see in the previous. So this is the under modulated signal. Hope you can clearly observe the carrier waves also, which can modulate according to the message signal. So the next wave is critical modulation signal. So here we can observe the modulation index is 1. So now we can get this type of waveform. Okay, so here we can observe our lower amplitude touching the origin. So here we are getting the waveform like this. So here we can clearly observe the inner waves also. So this is our critical equation, critical modulation. So next, when the modulation index is 1.5, we get these type of waveform. So here we can observe this extra sideband. So this are over modulation waveform when the modulation index is 1.5. So here also we can clearly observe the envelope. So but if we want to observe the envelope shape clearly, we have to increase the frequency level. For that, I have increased the frequency level from 100 to 1000, so that we can clearly observe the envelope shape. So here, if we observe the envelope shape, we can clearly get that same shape for the under modulation. So this is the under modulation signal. So these are a critical modulated signal. So here also we can clearly observe the envelope shape. And finally, these are over modulated signal. Okay, hope you observe the envelope shape clearly. And here we can conclude that after deriving the equation also, we are get the same waveform. So for the two different forms of equation, we are getting the same waveform. Hope you observe the shape of the waveform. So here we conclude that for both the equation, for this equation and for this equation, we are getting the same waveform while we are generating this both equation in the GeoGebra platform. So after deriving this equation, also we are getting the same waveform. So only difference is here we can get the three different term like the carrier, upper sideband and lower sideband. So here we can't differentiate the upper sideband and lower sideband. So that is a small difference between these two equation, but we are getting the same waveform only. And thank you for watching this video.